Hello folks, this is Doug, and in this third video about the ideal gas law, we're going to look at applying the gas law to gases that are in chemical equations. So we're going to combine stoichiometry with the ideal gas law. So we're looking at this last part right here. We're going to use the gas law in a chemical equation. If you have not watched the previous two videos, I highly recommend that you do. They'll help contextualize this a lot, because I'm just going to kind of assume that you've watched those previous two videos. So the ideal gas law problems, if you're going to use it in a chemical equation, really the big idea here is that you're still going to use stoichiometry, right? You still need a chemical equation that's balanced, and you're going to do the ideal gas law to find out how many moles there are of something, right? Because once we know how many moles there are of something, we can use a mole-mole ratio to figure out how many moles of other things there are in that equation. For example, if I was to ask what is the pressure in a 0.5 liter container after 12.84 grams of calcium carbonate completely decompose at 250 degrees Celsius, right? So what is the pressure after a certain amount of calcium carbonate decompose? And I gave you the equation here, right? So calcium carbonate turns into calcium oxide and carbon dioxide. But you'll notice that I have a solid, and a gas. So I can use information about gas properties like temperature, pressure, volume, those sorts of things to figure out how many moles there are of a gas reactant or product in an equation. So I'm going to do this one, and I'm going to walk through it and show you how we can use all this information, right? Because when I see this, when I hear what's the pressure, and I got a volume, and I've got a temperature, I'm thinking gas. This sounds like a gas problem, and sure enough, I have a gas as a product. So this is probably a question where I'm going to use my ideal gas law and stoichiometry to figure out an answer. So this question, right, here's the question. Basically, it's saying, what is the pressure, right? That's really the question. What is the pressure? And it's talking about of a gas, right? What's the pressure? The only gas I have is carbon dioxide. So it must be that I'm using my PV equals nRT, right? It's asking about a property of a gas. Since I'm looking for pressure, I'm going to go ahead and divide each side by volume so that I get pressure equals the number of moles of that gas times the gas law constant times the temperature divided by the volume. And then I'm going to start putting in my variables. And almost immediately, right, I hit boom. I don't know how many moles there are. This doesn't say how many moles, right, how many moles of CO2. I don't know how many moles of CO2 there are. So I'm going to have to do some stoichiometry. I'm going to have to figure that out. But I'll go ahead and I'll continue the rest of this. So I'm going to use my gas law constant, 0.0821 atmosphere, excuse me, times mole Kelvin, times my temperature, apparently it's 250 degrees Celsius. So if I'm doing the temperature, 250 degrees Celsius, right, I'm going to go ahead and I'm going to add 273.15 to that so I can get the Kelvin, which gives me, let's see, about 500, is that right? 523.2 Kelvin. So I'll put that in, 523.2 Kelvin. And my volume, they just flat out gave me and said that it's a half a liter. But what I'm missing is the number of moles. So I have to figure that out. I want to know what's the moles of CO2. I don't know the moles of CO2. What is known, and here comes my stoichiometry, what is known is that I have 12.84 grams of calcium carbonate. What's unknown, what I want to know, is how many moles of CO2 are there. And what conversion factors might I need? If I look at this, what conversions might I need? Well, I've got a mole. They gave me a mole rate, or a molar mass. So 100.087 grams of calcium carbonate are in 1 mole of calcium carbonate, right? That was just given in the equation. I could have figured that out, right? I could have added carbon and calcium and 3 oxygens. And then I know also, like I always do, right? I know the mole ratios, and I got to check to see if this is balanced. And if I do a quick check here, yes, it is balanced. So it looks like there's a 1-to-1 ratio here. Right? For every 1 mole of calcium carbonate, it releases 1 mole of carbon dioxide. And I think that's all I need. I don't need to find the molar mass of carbon dioxide because I'm not trying to get to grams. I'm just sticking with moles. Just sticking with moles here. So I think that might be all I need. So let me put this together here. Let me put this together. So I'm starting with 12.84 grams of calcium carbonate. I know that if that decomposes, that's going to turn into so many moles. And for every 1 mole of calcium carbonate, that's going to give me 1 mole of carbon dioxide. Or in other words, I can figure out how many moles of gas I should have. And if you calculate that all out, you get 0.1283. So that is this number, right? This number is the moles of CO2. So then I can just plug that in there. Apparently this is, let's see, 0.1283 moles. And if I plug that all in, enter it, it looks like I get 11.0 atmospheres. That's what the pressure should be in that container if 12.84 grams of calcium carbonate decompose, making carbon dioxide to fill that container. So that's what that's how many atmospheres should be in there. So that's how we're approaching that, right? So you can see how I kind of had 2 different problems, right? I combined 2 different things. I knew something about the gas, or I wanted to know something about the gas, but I knew something about the calcium carbonate. So I had to do some stoichiometry so I could figure out how many moles of calcium carbonate there are. Once I knew that, I could use my ideal gas law to figure out what the pressure was. So that's going to be the theme for a lot of these questions, right? We're going to use stoichiometry to relate to chemical species, either 2 products, 2 reactants, or a reactant and a product. And then we're going to use the ideal gas law to complete the problem. So let's look at another example. An Erlenmeyer flask is filled with 0.0502 liters of a hydrogen peroxide solution at standard temperature and pressure. A balloon is fitted over the opening and a catalyst is added to speed up the decomposition. The balloon rapidly fills to 5.51 liters. That's quite a bit. What is the molarity of the initial solution? And here's the equation, right? Hydrogen peroxide, which is aqueous, turns into liquid water and gaseous CO2. And again, right, here's an equation. One of the species in it, in this case a product, is a gas. But I'm gonna have to use my stoichiometry to help me figure this out. Ultimately, the question says, what is the molarity? So I'm going to solve for molarity, right? I know that molarity is going to be the moles of hydrogen peroxide over the liter of hydrogen peroxide solution. So I need to find those 2 things, right? Just like I do for any molarity problem. The liters, that's easy. It was given to me. They flat out said it was 0.0502 liters, right? That's what they said up here. They told me that's what the hydrogen peroxide solution was. My problem here is that I don't know how many moles of H2O2 there are. I don't know yet. Nothing in here tells me. I don't have grams of H2O2 that I can just convert. I don't know. What I do know is all the stuff about the gas. What I do know is a ton of stuff about oxygen. And if I know how many moles of oxygen there are, I can figure out how many moles of H2O2, of hydrogen peroxide there are, using stoichiometry. So what I'm going to do to get this moles of hydrogen peroxide is figure out what's going on with my gas so I can relate the 2. So in my second step here, right, I'm going to use my ideal gas law, my good old PV equals nRT here. So I need to know the moles of O2. So I'm going to use PV equals nRT. I'm solving for moles, so I'll go ahead and divide by RT so that those cancel out. So my number of moles equals pressure times volume divided by the gas law divided by temperature. What's the pressure of the gas? Well, it's going to be, since it's a balloon, it's just going to be the pressure of the room. So apparently atmospheric pressure, or in other words, the pressure we started off with, which was standard temperature and pressure. So this is just going to be 1 atmosphere. Right? Balloons, as a side note, balloons under normal conditions, right, are just going to be 1 atmosphere because a balloon always equilibrates with the atmosphere that it's around. So if you're just at normal conditions, a balloon's pressure is always going to be 1 atmosphere. If you put a balloon in like a weird chamber that had a higher, lower pressure, it would match that. But balloons are stretchy, so the inside pressure always matches the outside pressure. Anyways, 1 atmosphere. We're at STP. The volume, I see that the volume filled to 5.51 liters. So I've just popped that sucker in. R, I'm just going to pick, again, I like this R, so I'm going to pick this one, right? Because that's just the easiest one to do. I'm going to make sure everything's in atmospheres and kelvins. And then my temperature, again, is at STP, so I need to figure out what my temperature was. Remember that STP, like we said, it's always 1 atmosphere, and it's always 273.15 Kelvin. All right, 0 degrees Celsius. And so that's going to tell me how many moles there are. And if you calculate all that out, what you're going to get is 0.245 moles of O2. Now that doesn't really help me for up here, right? I don't need to put moles of O2 up here. I'm trying to solve for how many moles of hydrogen peroxide are in this solution. But thank you, stoichiometry, if I know how many moles of O2 there are, I can figure out how many moles of hydrogen peroxide there are, right? Because I have these mole ratios. So if I'm going to do this mole ratio business, first thing I have to do, right, every time you do stoichiometry is make sure you have a balanced equation. Is this equation balanced? Nope, it's not, right? I got 3 oxygens on the right and only 2 on the left, so I got to balance it. You can pause right now and balance it yourself, or I'll just tell you what it is. It's 2 peroxides, 2 waters to 1 O2, right? So now we're nice and balanced. 4 hydrogens on the left, 4 hydrogens on the right, 4 oxygens on the left, 4 oxygens on the right. So now I can set up my stoichiometry. I'm going to start with the 0.245 moles of O2. According to my stoichiometry, for every 1 mole of O2, there are 2 moles of H2O2, right? There's 2 moles of hydrogen peroxide, right? Because I'm going from here to here. It's a 1-to-2 ratio. And that's all I need. I don't need any grams or anything for this, right? Because I'm just trying to figure out how many moles of H2O2 there are so I can figure out that molarity. And so it turns out that this is just twice that, so 0.490. And then I get to plug that number back up into here. So now this turns into 0.490 moles of H2O2 over 0.0502 liters. And that's going to equal 9.77 moles per liter. And that would be my answer, right? This is my answer to the question. It's saying, what's the molarity of that solution? If when you decompose it, it fills up this balloon, that's the molarity. So it's kind of a clever way you can figure out the concentration of a solution. There's also titrations and stuff, but here's one way you could have figured it out. Let's do one more. I want you all to do this one. Okay, so let's take a look at this problem here, right? So we have a 2.5 liter reaction vessel that is filled with hydrogen gas at room temperature, and we're saying that room temperature is 22.1 degrees Celsius. And then during the reaction between hydrogen and limonene, which is a terpene found in citrus fruits like oranges, the pressure in the reaction vessel drops from 4.20 atmospheres to 4.0 atmospheres after returning back to room temperature, 22.1. The question is, how many grams of limonene reacted? And so I have this equation down here for you, right? Limonene is this first formula. And then we have our hydrogen. And they combine to make this product, some sort of reduced terpene thing. And so what I want to do is stop for a second. I will let you take a shot at this, right? It's just like the other problems where we need to use the gas law to figure out the number of moles of something so that we can use stoichiometry. So I'm going to stop talking. And I want you to take a crack at this, and then we'll go over it together. So now if I look at this question, right, they want to know how many grams of limonene, right? That's the thing that we're trying to find out. We want to know how many grams of limonene there are. But I don't really know about how many grams of anything else there are or moles of anything else there are directly. What I do know is I know lots of information about the hydrogen gas. Right? There's lots of information known about this hydrogen gas, right? I'll put lots of info about the gas. Right? We know the temperature, we know the volume, we know the pressure change. So lots of info about the gas. So I'm going to start with my ideal gas law, right? Our good old PV equals nRT. And what I'm going to do here is I'm going to figure out how many moles of H2 there are, because then I can use stoichiometry to figure out then therefore how many moles of limonene I must need. So I'm going to go ahead and I'm going to rearrange this so I can solve for moles. So I'll divide each side by RT. So then now I've got my number of moles equals PV over RT. And so let's start figuring out what we know here. So the pressure, so I've got two pressures here, right? I've got 420 to 4 atmospheres. Now notice that the question might be, well, which one do I use? Here we're using pressure as a way to measure the change in the amount of hydrogen, right? Hydrogen's being consumed, which is why the pressure drops. So really we're looking at the change in the number of moles of hydrogen. So I'm looking at the change in pressure here. And if I look at the change in pressure, according to this, it's just 420 minus 40, or in other words, 0.20 atm, atmospheres. Sorry, I should say, nope, that's right. So I'm going to go ahead and put that in for my pressure, right? It's a change in pressure, but still that'll allow us to talk about the change in the number of moles. And so I've got 0.20 atmospheres. They flat out tell me that the size of the reaction vessel is 2.5 liters, so 2.50 liters. My R, use the same old gas law constant that I always like to use. Just come back to my home base here. And then lastly, the temperature. I need to figure out the temperature. Remember that this gas law constant has Kelvin, not Celsius. So I need to convert my Celsius into Kelvin. And I've got 22.1 plus 273.15 equals 295.3 Kelvin. So I'll put my 295.3 Kelvin in here. And then when I do my math, I should end up getting that the change in the number of moles equals 0.0206, but if I count for sig figs, that is going to be 0.021 moles of H2. Right? So apparently that's how many moles of hydrogen, of H2, of elemental hydrogen, were consumed during this reaction. And once I know that, right, once I know what's going on with the amount of hydrogen, now I can infer what's going on with limonene. So I'm just going to set this up like a normal stoichiometry problem here. Right? So I'm going to put my known amount, unknown amount, and write out my conversion factors for me to think about. So for this one here, right, I know my known amount is the 0.021 moles of H2. That's going to be my starting amount for this equation. The unknown amount that we're looking for is grams of limonene. So grams of this C10H16. And then for the conversion factors, right, I know that every time I do stoichiometry, I need to have a mole ratio. So I need to go back to my equation, make sure that it's balanced, see what my mole ratio is. And if I look back at this equation, I see that it is not balanced. I need 2 moles of this H2, right? Because there's 4 more hydrogens on the right-hand side. And that's really it. That's all I need. So I've got my 2 moles of H2 for every 1 mole of C10H16. There's my mole ratio from my equation. And I think the only other one I'm really going to need is the limonene, right? They gave that to me, the 136.24 grams of C10H16 for every 1 mole. And I think that's going to be really all I need. So let's just go ahead. And again, if you're not too sure if you need more, I mean, by all means, put more if you think you might need it. I think I'm good here, and we'll just find out. We'll start putting stuff together and see if it is, in fact, all we need. So my starting amount is 0.021 moles of H2. I know that for every 2 moles of H2, I need 1 mole of C10H16. But that's not the amount that they're looking for grams. So I need to just convert my moles of the limonene, the C10H16, into grams using that molar mass. So that I get the grams of the C10H16. And if you punch that into your calculator, you should end up getting 1.4 grams of limonene. And so that's how you'd solve for those, right? So I think these are kind of interesting, kind of fun, right? You get to use the ideal gas law, you get to use stoichiometry, which you know really well at this point. So that's how you use the ideal gas law in equations. Please practice. Let me know if you have any questions. Happy studying.